Section 2.5, Cardinality of Sets. So sets A and B have the same cardinality denoted with our little symbol if and only if there is a one-to-one correspondence or a bijection from A to B. If there is a one-to-one function from A to B, then we can write that the cardinality of A is less than or equal to B. I encourage you to go back and look at our definition of one-to-one or injective for that to sink in. If the cardinality of A is less than or equal to the cardinality of B and the cardinalities are not the same, then we can write that the cardinality of A is strictly less than the cardinality of B. Now, where this comes to a head is with infinity. So let's first talk about countable sets. If a set is finite or has the same cardinality as the positive integers, then A is called countable. Otherwise, it is uncountable. So we're getting ready to deal with infinite sets here. This is the kind of lecture where when you get done, just go sit under a tree. Don't think about it too hard, though. Every mathematician that studied infinity did not suffer or did not they didn't have the best of fates. When an infinite set S is countable, we say that that set's cardinality is equal to aleph null. So what we're trying to do then is talk about the two different types of infinity. There's a countable one and there's an uncountable one. And the countable one has a structure because we can map it to the positive integers. So let's see this in action first, and we'll talk about kind of the results of this concept as we go along. So the set of positive integers is a countable set. Let's try and prove this. Proof. So we're going to let E be our set of negative integers, or sorry, just our set of even integers. Not sure why I said negative there. So 2, 4, 6, 8, and so on. And we're going to define a function. We're going to let the function f of n just be equal to n over 2. So this function f will go from our set of evens to the positive integers. Now I need two things to happen here. First, I can conclude that f is injective. Why? Well, if f of m were to be equal to f of n, that would be making the conclusion, that would imply that m over 2 would be equal to n over 2, right? Because that's what the function f does. Well, multiply both sides by 2. This would imply that m is equal to n. So it's injective. F is onto or surjective. Recall the definition. I'm going to let k be any positive integer. F of 2k then will be equal to 2k over 2, which is equal to k. So I can always find a preimage of k. That preimage is 2k. So surjective. Therefore, F is in one-to-one correspondence, or F is a bijection from E to the set of positive integers. So we can say the cardinality of E is equal to the cardinality of the the positive integers. Therefore, E is countable. Take just a second to appreciate what we've just shown. This means anytime you're dealing with a question that involves the even integers, the even positive integers, if you wanted to, you could apply this bijection first and make it a question about the positive integers. And that's also, there's some small part of you that wants to say, wait a second. All integers, all positive integers, that has to be bigger than just the evens because it feels like the set of even positive integers is quote unquote half of the set of all positive integers. But this disproves that. You can map them, right? That's the weird thing about infinity. Let's come over here to the side for just a second. I want to go ahead and write a little bit more work down because we're going to need to see something similar to this for a later problem. And I want to see it on I want to have an example of it on the easier problem first, just like we did when we were doing our definitions of functions. I'm just going to show you what this mapping looks like. So this mapping is going to take 2 and map it to 1. It's going to take 4 and map it to 2. It's going to take 6 and map it to 3, 8 and map it to 4, and because it's a bijection, those mappings will go both ways. So the set of even positive integers is countable. Next, an infinite set is countable if and only if it is possible to list its elements in a sequence. We just kind of saw this. We know that E was the set 2, 4, 6, 8, and we can list it in the natural ordering there, 2, 4, 6, 8, yada, yada, yada. And this is where we let the sequence be given by our function. And in some ways, this part right here is really the trick. If you're a countable type of infinity, you have an ordering. So let's try another thought experiment here. Hilbert's Grand Hotel. The Grand Hotel has a countably infinite number of rooms. Every room is occupied. So we have an accountably infinite number of rooms. Every room has someone in it. So we're booked up. A new guest arrives. Can we accommodate the new guest without kicking out someone? Yes. Even though every room has someone in it, all we need to do is ask each guest to move down one room. Because there's always another room. Give the first room then, because now it's empty, to the new guest. So even though I preface this by saying we have no more rooms, it's got this sort of, because of the ordering, we can ask everyone to shift down. There's always another room, and you create this opening. So it can show that it's just really difficult to consider the ramifications when dealing with infinity. The set of all integers is countable. So for this one, it's a little trickier, but what we're going to do is we're going to put a natural, not a natural, we're going to put an ordering on them. I'm going to show you they can go in an order, and I'm going to say, so it's countable. Z, here's the order I'm going to give it on. 0, 1, -1, 2, -2, 3, -3. So now I'm mapping something that feels bigger onto something that's going to feel smaller. If you want to see it, here is the function that will do this. N over 2 if even, and negative n minus 1 over 2 if odd. The tricky part here is this function that I'm giving you is technically a mapping from the set of positive integers over to the set of integers. However, it creates a bijection, so you can go the other way. It's just a lot harder to define. Finally, sorry, we have two more. The set of positive rational numbers is countable. Recall the definition of rational numbers. So the issue here is that they kind of go off in each direction. So let's write them down. 1 over 1, 2 over 1, 3 over 1, 4 over 1, 5 over 1, and the issue is it keeps going that way forever. So it's just me changing the numerator. What happens if I start messing with the denominator? 1 over 2, 1 over 3, 1 over 4, so forth and so on in both directions. And the question is, can I put these in some sort of an order? And the order I'm going to create here is some sort of a zigzag where I'm going to skip the duplicates. So the function here is going to be incredibly, if not impossible, to define. So we're going to set that aside, at least for us. And we're just going to focus on the visual of it. So we're going to start right here. We'll go down to a half. Then we'll go up to 2 over 1. And then we'll go over to 3 over 1. Then we're going to hit 2 over 2. That's a duplicate. We skip duplicates. 1 over 3. 1 over 4. 2 over 3. 3 over 2. 4 over 1. 5 over 1. And then we hit a string of duplicates. But this is what we're going to do. We're going to keep zigzagging up and down this. And so with this mapping, with this ordering, we can map to the set of positive integers. I can say, even though it's hard to imagine, this is the first rational number. Here is the second rational number. So let's go to one where it's not possible. The set of real numbers is uncountable. Proof by contradiction. suppose the set of reals is countable. Well, then we're going to zoom in on a very small part of it. If it's countable, the interval from 0 to 1 should be countable. If it's countable, thus the real numbers can be listed in a sequence. So let's write that sequence down. Here is the first real number in the interval 0 to 1. I don't know what it is, but it's between 0 and 1, so it starts out with a 0, and then it's followed by a bunch of decimal numbers. 1, 1. There's the first decimal, there's the second, here's the third, so forth and so on. Then here's the second real number in this interval. This is the second one, first digit, second one, second digit, second one, third digit. And I keep doing this. I define all of them this way. Third one, first digit, third one, second digit, third one, third digit. So keep in mind that each one of these is just a digit. So the DIJs in this case are 0, 1, all the way through 9, right? Just a decimal digit. So what I need to do is I need to show that there's something not in this list. So here's what I'm going to do. I need to make sure that the new number I'm forming is different from every other conceivable number on this infinitely long list. So I'm going to form a new number. I'm going to call it y. And it has digits y1 through y2, or y1, y2, y through infinity. Now, the trick here is that each digit is going to be different. The first digit, the first decimal, will be different from the first real number in the first digit place. So I'm going to let it be a 3 if the II digit for the ith number is equal to anything but 3. Now 3 is totally arbitrary here. I just need to be different. So as long as I don't see a 3, I'm going to make it be a 3. Otherwise, I'll let it be 7 if it is a 3. So I go and I look at this first number and I say, hey, are you the first real number in the first digit place? Is it a 3? If so, pick 7. If not, pick 3. So now it's automatically different from that number. So it's not the same as the first real number. Do the same for the second. If that underline there, if the second digit in the second real number, right, is a 3, pick 7. If it's not a 3, pick 3. So what I can see here is that y is not on the list. Y differs from xi in digit I. Small mistake here. Sorry. Kind of jumped the gun here. I said that part out loud. This part follows. Y differs from xi from each thing in the list in the ith digit. So y is not on the list. Contradiction. Now, why does all this matter? Well, as you might imagine, computer science course, we can handle the reals, but they're a lot more difficult. So what we like to do, what computers are better at handling, is something that is countable, that can be placed in an order. So we need to be especially careful when we're dealing with any sort of algorithm or program that deals with the real numbers.